Okay, let's continue with our work on integrating data. All right, really, oh man, that spelled terrible. Integrating, integrating. Okay, whatever. All right, really an important technique for data processing, and probably good to talk about some integrating options. Now, yes, MATLAB probably has some integrating functions, but you need to know what those functions are doing in order to use them. All right, so let's just talk about integrating. Remember, integrating is calculating the area under a curve. And the curve can be any set of data on the x-axis and the y-axis. Typically, we do time when we're looking at time domain data, and then this would be magnitude of some parameter. But it might be something else. It might be displacement and force, or it might be velocity and force, something like that. It could be very different. And you can still integrate those data, but you got to just be careful in terms of what you're getting when you're integrating different sets of units. Okay, and it's just the area under the curve. That's all it is. So we already know calculating the area under that equals area, I didn't spell it right, base times height. This is the base, and this is the height, or delta x and delta y. Okay? Man, I've been doing too much reliance on, let's just do this. Oh, make that a nice box. All right, yeah, that's what that was. Area equals base times height. Okay, area equals base times, oh, now it looks like I'm confusing the issue into a 3-dimension. If I was doing 3-dimension, I would just need to do volume, and I would add in the 3rd dimension. So now I'm just crossing that all out. That was just a total mess. And that's going to scan bad, and if you have to print this up, that's going to take up all your ink. Sorry about that. All right, so that's one way to do this. And when we look at a data set that we record, like, and I'll do acceleration now versus time, and we've got an acceleration profile that looks like that. And remember, if FS, and that's going back in time, my goodness, it's late. This is not, if FS is really something really high, okay, we get individual data points that are really hard to distinguish from each other. And in reality, I'm going to draw this an extreme, all right? This could be our first rectangle. This could be our next rectangle. The delta t's are all 1 over fs, okay? I'm trying to keep them the same. This, oh boy, I'm not doing good here. This is that one. And by using a rectangle to approximate that curve, you can see we're actually going to be calculating the area under, in reality, this curve. Okay, we're using this curve here. When I use a rectangle to approximate the curve, and that's base times height for this one, this one, this one, and then we just add those up. So base times height 1 plus base times height 2 plus base times height 3, and so forth. Okay, that will integrate this data set. Now, the key is get this sample rate really high, and then that delta t is so small that the margin of error is really small when you're integrating this data set. But it's still there. It's still there. So another way to do this is not to use a rectangle, but use a trapezoid. Okay. So let's go do a trapezoid. I'll go back to my other notes here. And let's say I've got a data set with a data point right here and a data point right here. Maybe it's this section right here or this section right here. Well, another way to do this is rather than draw a rectangle, I can connect the dots and then I can come up from my base 1 and back down to my base 2. So this would be x1, x2. This is still delta x, but now I've got a trapezoid, all right? And let's just do it the long way. I really have a rectangle with a triangle sitting on top of that. Remember, a triangle is 1/2 base times height, and our rectangle is base times height. And to get the area under this curve, starting here, up to here, over to here, and back down, that area is those added together. So I'm just put a plus sign there. All right, so that is maybe better than if I just approximated a rectangle here for these data points. All right, so now let's do a little bit of algebra. And let's calculate the area under this portion of the curve. And we do area equals 1/2 base, and I'll call that delta x times height, which is this height right here, or y, this would be y2, and this would be y1. So 1/2 base, x2 minus x1 times y2 minus y1. That will give us that height of that triangle. That's the triangle part. Plus the rectangle part, which is base delta x times the height of this. Now, in this case, because it's a rectangle and this is going to be 90 degrees, 90 degrees, I can use either x1 or I can use either y1, or I can calculate this height here, but I already have height here. This height is the same as that height. So I'm going to put y1 right here. And this is the rectangle. Okay, well, let's reduce this. Let's do a little bit of algebra. Let's see. What I'm going to do, I'm going to move delta x is common here. So I'm going to put delta x times 1/2 y2 minus y1 plus y1. It's just doing algebra. Let's distribute the 1/2 in here. So I have delta x times y2 over 2 minus y1 over 2 plus y1. I'll do 1 here. Now we can just quickly multiply that by 2. I'll do it the long way. Delta x. I want to add these two together. y2 over 2 minus y1 over 2 plus 2y1 over 2. Let's reduce it again. y2 minus, excuse me, over 2. Negative y1 plus 2y over 2, and now we can do that, and I get plus y1 over 2 or delta x. y2 plus y1 over 2. And that is the area for a trapezoid. Oh my gosh, can I spell it? Trapezoid. So instead of using a rectangle, maybe a better way to integrate these data is to use a bunch of trapezoids. And again, I'm just going to connect. The width is the same because the sample rate is the same. And all these are trapezoid. Oh, I messed up there, of course. And you can see that trapezoid actually follows that line probably better. And again, if we really have a high sample rate, these delta t's are so small that we're not going to see much gap between the data points. So, you can use a trapezoid. Interestingly enough, take a data set that we work with and get your sample rate really high, like 1,000 hertz, you won't find a big difference between using a rectangle or using a trapezoid. Either one tends to work, right? But now if you're picking a function in MATLAB using a shape to integrate, now you'll know why. You have some options of either using a rectangle or a trapezoid. Okay, that's a little bit more in integrating. Thanks.